Welcome to APCV 320 Computational Thinking and Doing. This week we will talk about Introduction to Computational Thinking. Lecture slides were adapted from Professor Henry Wershon, Applied Computing and Computer Science Program Director, who taught this class during the fall semester of 2020. The specific term computational thinking was first used by Seymour Papert in 1980 and again in 1996. Papert talked about children using computers as instruments for learning and for enhancing creativity, innovation, and solidifying computational thinking. He was largely dismissed as the idea of an inexpensive personal computer, one for every child like a notebook and a pencil, was science fiction back then. Today, Papert is considered the world's foremost experts on how technology can provide new ways to learn and teach mathematics, thinking in general, and other subjects. 10 to 20 years later, the term computational thinking was further elevated by Janet Wing. She published a paper in the journal Communications of the ACM, the Association for Computing Machinery. In her paper, Wing proposed the grand vision that computational thinking would be a fundamental skill just like reading, writing, and arithmetic, used by everyone by the middle of the 21st century. In her original 2006 publication, Wing defined computational thinking somewhat informally. She stated that computational thinking draws concepts from computer science to solve problems, design systems, and understand human behaviors. In a 2014 paper, she further refined the concept of computational thinking, including its application to various domains and how it can benefit society, especially education. Both her 2006 and the 2014 papers are well worth the read as reading assignments. So to summarize her definition, computational thinking is the thought process involved in formulating a problem and expressing solutions in such a way that a computer, which could be a human or machine, can effectively carry it out. There are two important concepts to computational thinking. We call them abstraction and automation, or some other people, they call them the two A's of CT or computational thinking. Abstraction focuses on essentials, ignoring irrelevant details. So note the relationship between computational thinking and computer science. So in her 2006 paper, Wing stated that computational thinking draws concepts from computer science and that computer science actually is the science of abstraction. So it focuses on creating the right model for a problem and deriving the appropriate techniques to solve that problem. Abstraction in computational thinking helps to formulate problems and express solutions. So there can be a hierarchy or multiple layers of abstraction. For example, think about a mobile phone app, right? So to you as an end user, the mobile app is just an application characterized largely, perhaps solely, by its user interface, or what we call the UI, right? In actuality, it's designed and implemented by different separate components, all of which are abstracted to you as a user. So think about the user interface, the data back end, perhaps business rule processing is implemented within the application. As a user, you can interact with the mobile app while being completely abstracted from the underlying data back end or business rules. With abstraction, we can transfer problems and solutions from one domain to another. We will cover an example of this later with the concept of the shortest path based on a graph model, which can be applied to the physical world. The other important concept to computational thinking is automation. Automation is based on solutions to problems or tasks that can be carried out by agents. The agents could be either a machine or a human. So computational thinking is conceptual. It's also about how humans think and process information. So the goal of the automation component of the computational thinking is to execute solutions based on different scenarios and to also abstract behavior as models or building block components. And remember, when we refer to a computer underlying, the automation process that can be either a human or a machine. Here is another definition of computational thinking by Liu and Fletcher, which states that computational thinking provides a conceptual way to systematically and efficiently process information in order to solve problems. This definition is particularly helpful because it provides the relationship between computational thinking and problem solving. As part of this week's discussion forum assignment, you will further explore the concept of computational thinking and share what you discover. Hopefully, you will find a definition or concept you can personally relate to and share, including why you like the definition, what you learned from the definition, and how you applied it. On the next few slides, we will go through an example of computational thinking. Computational thinking is a thought process. It's about how humans think. This is an example of a project that two students undertook for a previous class. They identified a school district which had hardware including printers, projectors, computers, mobile devices. All are located in different rooms and buildings across schools. And this is not even considering the possible proliferation of software across the school district. The school found that it was difficult to keep track of problems related to the hardware at these different locations. So the students proposed what's called a ticketing system solution to address the school's inventory problem. However, instead of building the ticketing system using very sophisticated programming effort or buying expensive commercial software, they built the ticketing system using the existing Google tools and additional third-party tools. This is a graphical view of the solution proposed and implemented by the two students. They integrated several tools available from Google. As a University of Arizona students, they had access to use and test the tools in order to address this particular problem. So using Google services and tools, the students built a website starting with Google Forms so that end user could report problems. They use Google Sheets to aggregate the problems reported by the end users, which is on the left side of the picture, using Google Forms. And then Google Sheet was also available for other users, such as technicians who manage the system and monitor devices at the different locations. The technicians, who are on the top right side of the picture, are able to check Google Sheets to analyze and identify common problems and to make decisions in order to monitor and manage the system efficiently and effectively. So Google Gmail, which is on the bottom side of the picture, is used to keep the end users who reported the problems up to date. This includes getting a confirmation email immediately after their problems were reported. Google Gmail is then used to immediately and automatically notify the technicians after problems were reported by end users. Last but not least, a third-party software package called UltraDocs was used to automate the whole system. It was used to automate email to both end user as well as the technicians who were managing the system. So this example is provided here for two purposes. First is to demonstrate how computational thinking can be applied to approach a problem based on abstraction and automation. Secondly, this example shows that computational thinking is not equal to programming. Many people misunderstood the concept of computational thinking and think that computational thinking is just programming. So later in the course, we are going to pursue programming in the Python and shell programming languages. It's important to understand that programming is just a tool that can be used to automate solutions developed by humans. This slide here shows some more information about the proposed and implemented solution, including the last three bullets related to costs. For any particular problem, there is usually more than one solution, so one must pay attention as to how to evaluate different solutions, of which cost may be the driving factor, or all other things being equal and cost as being the deciding factor. So how do we represent computational thinking? There are numerous benefits to representing computational thinking. When I say represent, another word that may be useful is to model. One benefit of representation is to document the problem and to document possible solutions that can be used to approach the problems. The problems and solutions can be revisited later if we document them appropriately upfront. Some programmers in many cases have to revisit the written code, especially when it lacks documentation, as they ended up having to reverse engineer their own logic. In other words, the time would have definitely been well spent properly documenting both the problem and the coded solution upfront. Another benefit is to communicate the problems and solutions to other people. Properly represented, it's easier to explain the problems and the proposed solutions. Another benefit is to compare solutions and determine which one is better and why. Or it could be that two or more solutions are equally powerful approaches to the same problem. Perhaps cost would then become a decision factor. Perhaps cost would then become a deciding factor. Yet another benefit of representation is to implement the solution. So think of a flowchart, which we will discuss later, and how it may be the basis of a pseudocode for implementation in a programming language. So in summary, think about representation in the context of the two important concepts of computational thinking: abstraction and automation. Abstraction is important to document the problem and represent the solution. Automation is used to execute solutions using agents, which can be human or machine. So, what are some approaches to representing or modeling computational thinking? There are several concepts listed here, which are by no means exhaustive approaches to representing computational thinking. Over the next few slides, we will go over some specific examples. As I previously mentioned, flowcharts are a useful model to represent computational thinking from both a problem and solution perspective. Flowcharts were introduced in 1921 in the American Society of Mechanical Engineers. In the 1930s, the idea evolved into industrial engineering curriculum. In the 1940s, the concept reached industry, and by the 1950s, model computer programs were represented and denoted using flowcharts. Nowadays, flowcharts are very useful in software engineering, medicine, chemistry, biology, economics, etc. Flowcharts can organize a thought process and provide the high-level views we need to abstract details that are not relevant. Take, for example, the process of an online order system presented on this slide. First, there is a start point for this online ordering process, and of course, there is a finish point. Right after the start point, the user is able to enter an order, and after the order is received, two parallel procedures kick off. One procedure is used to check whether the user provided a credit card is valid. The other procedure checks whether the ordered items are in stock. If the credit card is not valid, the order will be cancelled and the process will finish. If the items are not in stock, then the order will be cancelled and the process will finish. On the other hand, if the credit card is valid and the ordered items are available in inventory, i.e., if both conditions are true, then the credit card will be processed and the ordered items will be packed and delivered, and the online order process will finish successfully. Flowcharts can organize thoughts and can provide views that can abstract irrelevant details. The actions in flowcharts can be very complex, and the flowcharts can even be hierarchical. In other words, when the flowchart action block decomposing into an entirely separate flowchart. There are a couple of example flowcharts shown on this slide. I'm not a biologist, so I do not fully appreciate the meaning of the oxaloacetate on the flowchart. I'm not even quite sure how it's pronounced. However, I do recognize the lower left flowchart as being some type of a protocol flowchart. Being an electrical engineer, I can recognize some of the action boxes as being associated with the carrier sense multiple access, or what we call the CSMA, with collision avoidance, which is the CSMA/CA network protocol. As these diverse examples show, flowcharts can be used to represent the processes in mostly any domain. Another useful representation of computational thinking is a graph. This slide shows a couple of different graph representations with real-world applications. For example, the upper graph of nodes with vertex coloring, vertex being a node here, is used in various problem domains, including computer registry allocation, frequency allocations, scheduling, and even geographic map coloring. Minimizing the number of colors while maintaining the distinction between countries on the map is desirable. At the very simplest, the chromatic number of a graph provides some level of a presentation of how complex the problem space is and perhaps the resulting solutions. On the other hand, the lower graph example illustrates the concept of a spanning tree, which is used to model optimal network connectivity. In this representation, the goal is to optimize the network topology using the lowest sum of weighted links while avoiding any loops which can negatively impact network performance. The lighter weight black lines are removed to avoid loops and to minimize the sum of the remaining weighted links. This is a fundamental characteristic of what is known as the network spanning tree protocol. Yet another approach to representing computational thinking is the finite state machine. A finite state machine is similar to a flowchart and a graph, but it's more structured and rigid and thus more precise, more like a mathematical model. A finite state machine is composed of a finite number of states. So we will walk through the lower left finite state machine for a vending machine, and then we will discuss the advanced setup on the upper right side. So if you look at the state machine, finite state machine for the soda vending machine in the lower left side of the graph, you will see it's like starts with, we have a button for start, and then you can put the 25 cents, and then the system will show up that it contains 25 cents. Then you still have the option to return the money if you don't want to dispense anymore. So you can click money returned, and then the machine will go back into the start again. So you can loop through this circle forever, basically. And then if you put for the first time 25 cents and then you add another 25 cents, the system will say like, now I'm containing 50 cents, and this is the good enough to buy a, like a can of soda. And you still also have the option to either return the money, so you can go back to the start, or you can proceed further and you go to the desired flavor and only push that button. The required flavor will be dispensed from the machine, and then the machine is gonna go back into the start again. Now this is a fairly quick setup, so it's easy to do. But if you look at the other one in the top where you start, instead of just using 25 cents, we made it more complicated by adding the dime and the nickel to it. So we replaced the first two branches here from the start and system contains the 25 cents by this whole setup here from 0 cents to 5 cents to 10 cents to 15 to 25. So you can tell it's more complicated, but it does the same purpose now because you give more option by using the dime and the nickel besides the 25 cents. So in the nutshell, we can see now contracts the complexity of a finite state machine, which only accepts the quarters, like the one that we talked about in the bottom, with the one that will also accept nickels and dimes. So note that how the single lower left transition of the quarters only state machine from start to system contains the 25 cents. How does it expand to numerous state transition when quarters, dimes, and nickels are accepted, right? So conversely, think about how complicated the upper right state machine representation would be if the soda machine required 50 cents. Abstract machines are theoretical models of a computer used to describe problems computationally. This slide shows some possible abstract machines, but it's just by no means an exhaustive representation of abstract machines. Combinational logic is used in computer circuits to perform Boolean algebra on input signals or on stored data. Computer circuits normally contain a mixture of combinational and sequential logic, which means here the sequential logic depends on time, for example, current and past state. So for example, the part of an arithmetic logic unit or the ALU that does mathematical calculations is constructed using combinational logic. Of course, we just discussed the finite state machine on the previous slide that's composed of states and transitions that can change the machine from state to state. Push-down automation, which is a singular, also known by PDA acronym, is a type of automation that employs a stack. Push-down automata, which is the plural, are used in theories about what can be computed by machines. They are more capable than finite state machines, but less capable than Turing machines. Push-down automaton are often used in problem domains involving counting and matching. A Turing machine is a theoretical concept of a computer that has a processor and memory, which could be as simple as manipulating symbols on a strip of tape according to a table of rules, as you see in the tape in the bottom, the black one. You may be familiar with the Turing test developed by Alan Turing in 1950, which is a test of a machine's ability to exhibit intelligent behavior indistinguishable from that of a human. If the evaluator cannot reliably tell the machine from the human, the machine is said to have passed the test. So the concept of a Turing machine is that it can write programs that can solve problems. For example, it passes the test that the human passed, which in other words we call it the writing the code basically. Last, in the list of abstract machines, programming languages are really just general computers. They are abstract computers that make it easier for humans to approach and write programs that can solve problems. So let's review programming languages in more detail. Programming languages are abstract to machines, which is machines only understand binary ones and zeros, right? With the exception of state-of-the-art quantum computing. So programming languages can be categorized based on the paradigms used by programmers. In this slide, we show three categories used to classify programming languages. Note that is one view of categorization. So I tried to find an authoritative reference for this list and discovered many other means of categorization. For example, machine, assembly, high level, or object-oriented, procedural, etc. The Wikipedia page, which lists, a list of programming languages by type, it lists over 50 types. So I'll address this a bit more on the next slide. However, we will focus on the following paradigm grouping. So as you look in the on this example on the top, like how you go from like a high-level programming languages, which is C, using the compiler, and then from there, like you switch that into a through the compiler into a different sort of code. The compiler will do that basically, and then from there it's going to switch it into the assembly language, and the assembly language, it's the language that the computer understands, which is zeros and ones, right? And I encourage everybody here to click on this link where it says comparing C to machine language. It talks about an example, and he really explained that very well. And the example talks about Fibonacci numbers, how this code from a high level, and the way how he shows you like things, how they switch from that high level into the 0 and 1. So I encourage everybody to go to that YouTube and watch it. So as I said, however, we'll focus on the following paradigm grouping, which is the first is imperative programming languages, and the examples include a assembler, C, BASIC, Java, C++. And in such a programming languages, programs are composed of a sequence of instructions and commands. The instructions and commands can include assignment statements, loop statements, conditional statements. The program state is composed of values assigned to variables in the program. The second is functional programming languages, also referred to as lambda calculus. In functional programming languages, programs are just a set of function definitions which are applied to solve problems, to approach computational tasks. Languages in this category include Lisp, ML, which is meta language, Haskell, and the F#. The last is logical programming languages, and examples in this category include Prolog and the data log. So Prolog and data log. A program in logical programming language is a set of logical rules. So the driving force is based on recursion and a subset of first order logic. And this slide here, and by no means, this is just a side note, like for you don't need to do like really a deep dive, or to know like the details of this slide. It's another view of the taxonomy of programming paradigms. So you will note that the three primary paradigms that we discussed on the previous slide are called in the red dashed boxes here. If you look at the red dashed boxes here. So as you can tell that there is the imperative, the functional, and the logic programming are called out on those red dash boxes. So whoever knew there was so much breadth and depth to programming languages, for example, the entire field of theory of computations, it's really quite fascinating what we see here. TIOBE or TIOBE came from the word the importance of being earnest. It's a Netherlands company that maintains an index reflecting the popularity of programming languages. It's important to note that TIOBE index is not about the best programming language or the language in which most lines of code have been written. 25 search engines are used to calculate the TIOBE index. For this month, which is August of 2022, changes in the index has to do with the new Google language Carbon has been added to the TIOBE index, and Carbon debuts at position 192. The other thing you need to know that programming language for the TIOBE index have to meet three requirements. Number one, the language should have an own entry on Wikipedia, and Wikipedia should clearly state that it concerns a programming language. This is the reason why Ruby on, Rails, Excel, Android, Boost, Cocoa, ASP, and Ajax are not considered programming languages for this index. Number two, the programming language should be Turing complete. As a consequence, HTML and XML are not considered programming languages. Number three, the programming language should have at least 5,000 hits for the plus language programming for Google, like when you look it up when you do that query. So programming languages that are very similar are grouped together, and the rating is then based on counting hits for the search query. The index on this slide shows Python as a leader within the community, as you can tell right now from the blue index here. It also shows the trend for the past 20 years. It goes from 2002 to 2022. So looking back at the period from 2002 to 2012, you notice that Java was dominating the community. C also is a very popular programming language as well. For a single problem, there's likely more than one solution to approach it. You may have more than one programming language available for you to write programs when you need to approach a problem or design a system. So for example, if you need to conduct data analysis, you may want to use Python or the R programming language. R and Python are state-of-the-art in terms of programming languages oriented toward data science. However, R is mainly used for statistical analysis, while Python is more of a generalized approach to data science. So it all depends on what you are trying to answer. And it also probably depends on what language you know best. Similar to the Maslow's hammer phrase, M-A-S-L-O-W, hammer phrase. If all you have is a hammer, everything looks like a nail. So in computer science and programming, this is known as the notion of a golden hammer, which is a familiar technology or concept applied obsessively to many software problems. This concept was addressed in literature in 1998 as an anti-pattern for the programming practice to be avoided. And I encourage people to look into that as well. So, computational thinking is becoming a fundamental skill in many STEM domains, which is science, technology, engineering, and mathematics. Computational computation is not new, and it has impacted every area in science and engineering. It has become very important and has started to have an impact beyond the STEM and has become very relevant in the art and the humanity disciplines. There are so many high-level programming languages are available nowadays. By the end of this class, you will be familiar with at least 2 programming languages, and from there you will have the foundation from which to further learn and explore. It's important to re-emphasize that computational thinking is not about how computers think, it's about how humans think. The computers involved in computational thinking actually are not necessary to be machines, and they can be humans, and computational thinking makes it possible to combine powers of machines and the humans together and to solve some problems that previously human beings alone could not accomplish. This is the end of the lecture. If you have any questions, please feel free to email me.